All right, here we go again. All right, so we are in the atmospheric energy packet. We're in our second topic now. You've had an opportunity to check your independent practice work for your transfer of energy. So we're in a slightly different topic, but we're dealing more with radiation. So we're drilling in a little bit further to this topic so we have a better understanding of how that works. So we're on page 4 of the packet that you should access through the shared folder online. So you have the notes. ESN 6 is what you should have open, page 4. Eventually we will be using this, the electromagnetic guided practice, an independent practice, also the electromagnetism access point. So electromagnetism, what is that? Well, it's the light spectrum, right? Electromagnetic, we have two components. There's an electric component and a magnetic component to light, which is also part of the reason why we've discovered we can use something like solar cells. We have the ability to produce an electrical charge. There's some magnetism to it, so it's going to be able to push off electrons and move them and produce current. All right, so it's very cool, to say the very least. By the way, as we talk about this, the most important piece of infinite earth science knowledge is don't look at the sun. Don't. Right? Now I can actually put my disclaimer somewhere to be viewed. All right, so anyways, radiation transferred through no medium. That means it can transfer through anything. It goes from heat source to heat sink. Nothing in between touches them. There's no fluids, there's no solids. All right? So we've got sun, the sun, that releases all wavelengths of energy. Some of that energy doesn't make it to the surface of Earth because of our atmosphere, as well as our magnetosphere. Okay, so there's two reasons. Not all light makes it to the surface, but the sun does release everything from the smallest, which is gamma radiation, to the longest being radio. Yes, radio waves are light. Most of you are probably familiar with radio being, Z100, Alt 92.3, whatever is your thing. That energy that's being released out of the top of this Empire State Building, right out the window, which I point that out all the time, that is being emitted from the tower as a light wave. Now the light wave is in the radio frequency. Those devices called radios, they have an antenna, and that antenna absorbs that light wave, sends that energy down to be received and then transferred and converted into sound through a processor. So that is light that's coming into the device, and that device is creating the sound. Our phones also use a form of radiation, microwaves, to transmit signals from our phones to cell phone towers and back. So it's light waves, but we can't see that light. It's not visible, but it's within the spectrum of all light. All right, so let's talk about light itself. It is crazy fast, okay? We're talking, I got a little typo here. So 3.8 times 10 to the 8th meters per second. My little fingers must have been going somewhere else as I was typing this fast, okay? That's fast enough to circle the Earth, the globe, 8.5 times in 1 second. That's crazy fast. 1/1000 light has gone around 8.5 times. Nuts. All right, so let's talk about how we classify waves. We classify them based on wavelength. That means we're going to be going to measure a wavelength, and that is typically from crest of a wave to crest of the next wave. That distance in between, that is going to be the wavelength. And for most light waves, that wavelength is very small, okay? So frequencies. Frequency is a measure of the number of wavelengths that pass a point in 1 second, okay? So all light travels the same speed, but sometimes you've got more waves that are in that light passing at the speed of light. We'll get to what that means down below, okay? So we have to talk about the unit for that, which is hertz. Maybe you've heard of the car company, Hertz. I think they probably may have named themselves that because hertz is usually a very fast thing. It's light speed. That means they can get you service quick. All right. The abbreviation is capital H, lowercase z for hertz. All right. You also may be familiar as a child, Roy G. Biv, which is the order of colors that you might have been taught. You have your red, orange, yellow, green, blue, indigo, and violet. Well, I have to turn this little thing upside down if you're familiar with it. It's actually VIBGYOR. We tend to organize all light waves, including the light waves of color, from shortest wavelength to longest wavelength. So Roy G. Biv is a fun way to remember your order of colors within a rainbow, but really it should be VIBGYOR. All right, so that's our new friend now. All right, in terms of frequencies of light, we have to talk about how we calculate or measure or give hertz to light. So here we've got a low frequency, here we have a high frequency. And the way I'm going to discuss this with you is that from here to here, this distance, I'm going to say that it takes light 1 second in this example to pass through this distance. So instead of it being a distance measurement, I'm going to let you know that this distance can be traversed by light in 1 second. Why did I pick 1 second? Well, hertz is the number of wavelengths that can cross through a place in 1 second. So for this example, we are saying 1 second. So as I look here, I have a wavelength, another wavelength, and another wavelength. So I have 1, 2, 3. I have 3 wavelengths, so I have 3 hertz. Okay? If I look down here, I have about half. Okay, but let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, and half. So I've got 9.5 hertz. So if I were to figure out which one has a higher frequency, I have a higher frequency here because this value is measuring more wavelengths, more crest-to-crest wavelengths through here in 1 second than the light wave above. So one way you can sort of think about it if you're a boxing fan, and I'm not promoting fighting, I'm just saying if you're thinking of a boxer who's jabbing, right? If you're going to jab somebody 3 times in a second versus 9.5 times in a second, there's going to be more energy in this light wave. So even though both of these are traveling at the speed of light, this one packs in more energy. Okay? All right, so here we've got a few aspects that you should pause the video, read through, take a moment to see if you might be able to analyze them a little bit, and then answer them. So go ahead and pause the video, and we'll be right back to answer them. Okay, so I'm going to cover how to answer these questions. I hope that you tried to go to page 14 on your own in order to introduce to yourself this scale, but let's do the introduction together. So here we are, page 14 of the reference tables. I have my entire electromagnetic spectrum from smallest wavelength to longest wavelength. So go ahead and label that up on your reference tables. I've also chosen to use blue and red because typically as you move to a longer wavelength, you tend to be more on the red side. As you move more to the left, you tend to be more blue and violet, so that's why I'm labeling it in blue. That will come into even more play when we finally get to astronomy. We talk about the Doppler effect. Okay? So let's analyze. We've got gamma rays, X-rays, ultraviolet. They are all to the left and decreasing wavelength compared to visible light. The visible light that you are watching me here on this video right now only consists of wavelengths of light in this tiny little sliver section here, which has been expanded for you to see the order of colors as I had introduced you to the VIBGYOR, from violet to red. Then beyond, on the right, we have our infrared, our microwaves, and our radio waves. all in the increasing wavelength. I would also like to note that not just are they smaller wavelength, they are more intense. By more intense, we mean higher energy, okay? Higher hertz. Think of it like that. The higher the hertz, the more it's gonna hurt, okay? Like UV, right? Sunburns, or maybe the gamma radiation, or X-rays, things that you don't want to be exposed to on a regular, if at all, basis, okay? Infrared, microwaves, and radio waves are also risky in their own factor, but they tend to be riskier for different reasons, all right? Maybe we'll eventually talk about microwaves. So on the increasing length side, let's make sure that we also note the opposite relationship, that if it's more intense over on the left, with shorter wavelength, it's less intense on the right side. Please make sure you're adding this stuff into your reference tables. All right, so now if we were to try to compare and contrast the lengths of these, if I have something like microwaves and X-rays, microwaves are a longer wavelength compared to X-rays. It can get a little bit hairy here if we're looking at X-rays and we're trying to compare them to ultraviolet, but some ultraviolet can be a longer wavelength than X-rays because a section of this bar is further to the right in the increasing wavelength direction of the diagram. Okay, that works the same way when you're comparing even down here in your visible light. That if you're orange light, you are a less intense light than blue. It's the same reason why we in class have discussed turning your iPhone screens red at night, because it's less intense. It doesn't trigger the melatonin. It helps your melatonin regulate so that you feel maybe more relaxed before you go to bed versus leaving your screen pouring blue light into your eyes. Okay? Maybe one day we'll do the adulting club and we can talk about how to change your iPhone screen. All right, but really that's the comparing and contrasting. So let's get back over to here and answer these questions. So which has a higher frequency, green or orange light? Very similar to the example I just used. So we've got orange here, we've got green here. Orange is definitely a longer wavelength, green is a shorter wavelength. Orange is more intense, green is less intense when comparing just those two. Right? So higher frequency, green. Green is more intense, higher frequency, higher hertz. Right? More intense, higher hertz, higher frequency. Which are more intense, microwaves or infrared light? So let's go take a look and see. All right, we've got infrared and microwaves. We do have a little bit of overlap. But if we're trying to figure out which one is more intense, we have to look at which of these two boxes on the whole is further to the intense side. And even with this overlap, the majority of infrared is more intense than microwaves. Apologize for the way the board's writing. So infrared, not infrared. Okay, make sure you make that pronunciation accurately. So scientists just discovered a brand new kind of electromagnetic wave that has an extremely high frequency. Its wavelength must be very, well, let's go to reference tables. So if we are on the more intense side, what happens to the wavelength? The wavelength gets smaller. Right? It's a decreasing wavelength, so there's a higher frequency. So here, we would say that its wavelength must be very short. Okay? So we want to, in this graph here, we're going to graph the relationship of wavelength and frequency. So I don't mind which way you do it, but I'm going to choose frequency here, and I'm going to do wave length. And to help with viewing this, I'm going to use red for my quantitative values. So let's just say this is going to be low frequency, also a lower or small, that's a slash, small wavelength. Here we're going to say high frequency, and here we're going to say long wavelength. So if we're thinking about wavelengths, like what we had here in this diagram, if we have a longer wavelength, you're going to have a lower frequency because there's more space and it takes a lot more time to get more energy passed. So a long wavelength will be a low frequency. So long wavelength, low frequency. High frequency, short, small wavelength. So this is the general relationship trend line for frequency versus wavelength. Okay. All right, we are now to the independent practice. So you should be opening up this document here where you have electromagnetic guided and independent practice. Begin question 1 and 2. Go ahead and pause the video. If you want the access point, you can find that same access point in the shared folder. That is not the end of class. You get a little beep for old time's sake. All right, so hopefully you've paused. You've tried out this question. Let's read it together. Which diagram best represents the relative wavelengths of visible light, ultraviolet energy, and infrared energy? So we've got 3. Looks to me like this is compare and contrast. We have 3 diagrams for our choices as answers. We have 3 wavelengths we have to compare with: visible, ultraviolet, and infrared. So if we're looking and it's showing us frequencies or diagrams, examples of those frequencies, it looks to me like there is certainly a difference between those frequencies. We'd want to start analyzing which has a lower frequency, which has a higher frequency, which one might be somewhere in between. So I would say let's isolate what they each are over here and then compare what we have as options here. So visible, ultraviolet, infrared. Okay? Visible, ultraviolet, infrared. Fortunately, they've given us resources where our light waves don't overlap. So we won't run into a problem that some of them might be like the others. So if we look here, we have infrared on the right. We have this area in here, which is visible. Then we have ultraviolet to the left. So based on our scale, we have the shortest wavelengths go with ultraviolet, the longest wavelengths go with infrared, and visible is right here in between. So let's go back and label this up. So for ultraviolet, we know it is the short of all 3, the shortest of all 3. Infrared, we know, is the longest of all 3. And we know visible is in the middle. Okay? So then we're looking here to see if we can find which of these diagrams is going to illustrate for us that relationship. So let's just dive into ultraviolet, because it looks to me like the shortest wavelength is the top image of each choice. So ultraviolet, not there. Ultraviolet, not there. Not here. Here we go. Just to make sure that we aren't jumping to conclusions too quickly and we want to check our answer before we move on. Visible light, yep, that looks like it's kind of in the middle here. And then infrared is the longest wavelength with the biggest gap. So yes, it is indeed choice 1 in this case. All right, question number 2. Which type of electromagnetic radiation has the shortest wavelength? Very similar to what we just did. So you've got to take these 4 and figure out which one of these furthest to the left on the scale. Excuse me. All right, we got ultraviolet, gamma rays, radio, visible light. Ultraviolet, gamma rays, radio, and visible light. Looks to me like gamma. Gamma is the furthest one over. So in this case, I will choose gamma rays. All right, so now you're at the same place we've been in several lessons now. I hope that you are actually taking the time to go through the independent practice, Try it on your own, a few of them. If you get stuck, grab those access points, throw them in a new tab on your browser. Also, check the answers, follow up. If you have any questions or concerns regarding those questions or class, feel free to add a comment below on the video. And thank you for liking and subscribing.